Hey, hello. Hey, my name is Prasad. I'm the other instructor for this class. So I'll be lecturing for this one and the next one. We'll cover the topic of fast Fourier transform, and that'll wrap up divide and conquer, and then Satish will be back. So what we'll be covering in this lecture and the next one is a beautiful application of divide and conquer, and it's not only very beautiful, it's extremely useful and widely used. So much so that it's difficult to even point out all the places where it's used. For instance, if you pick up your phone, probably this FFT is implemented in the hardware, it's probably implemented in software, at various levels of the stack, and in various applications, in lots of places you would imagine FFT is implemented. So it's a really important algorithm, and it's one of those algorithms where lots of things fall into place, and everything works beautifully, and you have a really nice algorithm. So there are many ways to go at it. There's many ways to present this topic. It's sort of like a hike up a beautiful mountain. I'm going to take a particular route and take a particular route to the topic. But there are many ways to understand this, and lots of beautiful insights all over. So you're in for a treat. So let's start. So I'll start with polynomials. Okay? So all of us know what polynomials are. So let's just look at univariate polynomials. So you have a univariate polynomial. P of x is p0 plus p1x plus p2x squared plus p dx to the d, and the degree of the polynomial p is just d. Okay? So polynomials are the most basic objects after numbers, and you would use polynomials all over the place. So for instance, error correction, you might have seen error correction in CS70 uses polynomials. Cryptography, signal processing, any kind of pattern matching. It's literally graphics. So polynomials are ubiquitous. And you would want to do, you want to talk about operations on polynomials. So before we do that, how do we represent polynomials? The most simplest thing to do would be to write down a polynomial as a sequence of its coefficients. So the simplest representation that you can think of is just as a vector of coefficients. Okay? And so now we have one natural representation. So you just have a vector of real numbers or coefficients that give you the polynomial. Now, you want to see what kind of operations that you can do on it. So perhaps the most simplest operation you can think of is evaluating a polynomial. So here, what's the situation? You are given a polynomial p by the vector of coefficients. And then you're given some point, alpha. It could be real or complex or some number, basically a number. And you want to compute p of alpha. So you could be given for x cubed, and you want to compute p of alpha. And you're given alpha equal to 5. Okay? And of course, the most trivial way to compute it would be to say, okay, so p of 5 is 1 plus 2 times 5 plus 3 times 5 times 5 plus 4 times 5, 5, 5. Okay? Does it make sense? So, of course, this is a naive approach to compute this. And if you did this, you would take, how much time would you take? Like how many additions and multiplications would you take? Yes. Yes. O of n squared, yes. So you take you order of d squared, where d is a degree, or of, the quadratic time. Because, you have these numbers you need to compute, alpha, alpha squared, alpha cube, and you're taking alpha to compute alpha to the I, you're doing I multiplications. So your summation of I is quadratic in n. But, of course, that's wasteful, right? In order to compute alpha to the I, there are better ways to do it. So any way to improve the naive algorithm? Yeah. Oh, yes, that would be the most optimal thing to do. So the most optimal thing to do would be to use the Horner's method, which is to rewrite the polynomial like this. So this is called the Horner's method. Which is, you write p of alpha is, let me write it in this case, it's 1 plus alpha times 2 plus alpha times 3 plus alpha times 4. Right, or in general, if you want to compute p of x is p0 plus alpha times p1 plus alpha times p2. It's just a clever way of organizing the additions and multiplications, the order in which you do them, so that you minimize the number of operations. So in particular, if you look at this, you can check that the number of additions and multiplications is essentially d. So this is d additions and d multiplications. So if you want to remember, you would think of basically each evaluation as taking linear time. Okay? Okay. Yes, you had a question?
Can you also do it like
Yes, there are other ways to get, that works too, and there are many ways to get roughly order d time. There's an intermediate solution, which is to use fast exponentiation to compute alpha to the k for each k. That's d log d time. But of course, in this case, there's a really simple one. The Horner's method or variants of that you can get order d time. Okay, so linear time to evaluate at a single point. All right, so let's see what else we want to do with a polynomial. You'd want to add. Okay, you'd want to add two polynomials. You're given two polynomials, p0 and p and q, and you want to add them. Of course, this is kind of easy. What happens when you add them is you end up adding the coefficients, right? So the coefficient vector of the sum is just the sum of those two vectors. If you want to add two polynomials, you just add the coefficients. And of course, this, how long does it take? Well, this takes just order d time. Okay? So one thing I'm assuming in all of the lecture today and in this entire topic of FFT is we're going to assume that all the numbers are constant size. So each arithmetic operation takes a constant time. So each addition, multiplication takes a constant time. So that's going to be a running assumption all throughout this topic. So the assumption is each arithmetic operation in order one time. This is a typical way now. This is what happens typically with numbers on your computer. You have a 32-bit number and each operation, addition, multiplication is constant time. So that's going to be the way we'll work. Okay, so addition is easy. So let's do something more interesting. So let's try to multiply polynomials. Okay, so what happens next? So, okay, now we have two polynomials, p and q, and you want to multiply them. Right, so if you want to multiply something like this, right, the most naive algorithm to do this would be to just multiply every pair of terms, right? So the naive algorithm is multiply all pairs and add and simplify. Right, so in this case if you have a degree d polynomial p, there's a degree d polynomial p, you have d terms and you have d terms here, right? If you multiply them out, if you multiply every pair out, you get d squared terms, and then you simplify them, you add them up, you'll end up with a degree 2d polynomial. But the total computation you did was order d squared, because at some point you had d squared terms in your operation. That you multiplied every pair of terms in each of the polynomials. So the naive algorithm takes order d squared. Actually, d squared time. Is it clear? Okay, so that's okay. So what we'll see now is what we'll see in this lecture and the next is a very clever algorithm that gets d log d time to multiply two polynomials, order d log d time. And we'll do it in stages. So it's sort of our goal would be order d log d time. Okay. So, of course, polynomials are very basic objects. They show up everywhere. But one simple reason why polynomial multiplication itself is very important is polynomial multiplication corresponds to what's called convolution. It's basically the same operation as convolution of signals in signal processing. And the same algorithm that we develop for polynomial multiplication, you can use it for convolution. And of course, polynomial multiplication on its own will find applications in pattern matching and so on. You'll see more applications in your homework and so on. So let's step back and think about how to have a really fast algorithm for multiplication. And in order to do that, we need to step back and think about how we represent polynomials. So we sort of decided on this representation of polynomials, which is coefficients. But there's an entirely different way to represent polynomials, which has its advantages. So here's a different way to represent polynomials. You just specify points on the graph of P, right? Or alternately, I'll specify the value of the polynomial P at n points. So just to draw a picture, right? If you had a polynomial, you can always draw a graph for that polynomial, right? You can draw a graph. And instead of writing down the coefficients of the polynomial, I will tell you the value of this polynomial at n points. Let's say I'll tell you P of 1, P of 2, P of 3, P of 4, and P of n. Okay? So if you have, for instance, a degree 1 polynomial is just a line. When you draw a graph, it's a line. So I just need to specify 2 points on a line, and you know the line, right? And if it's a quadratic, if I specify 3 points on a quadratic, there's a unique quadratic that goes through 3 points. So that's another way of specifying the polynomial. Okay, so here we're going to use this simple fact that basically n evaluations uniquely determine the polynomial, a degree D polynomial. Actually, let me just use the same thing. D plus 1 evaluations uniquely determine a degree D polynomial. So as long as I give you more than D plus 1 points on the curve, you know what the curve is. So it's a different way of representing polynomials, right? Okay, so this is a very different way of representing polynomials. Let's imagine we have our polynomials represented like this in our inputs. Okay, so let's skip evaluation for now. Let's, for instance, look at addition. What happens to addition now? So what's happening now is you're given 2 polynomials, given P, not as a list of coefficients, but you're given a list of evaluations. You're given the value of P at n points, and given the value of Q at n points. Okay? You're given 2 polynomials by their curves. Okay? And so now, if you want to find out the representation of the sum of those 2 polynomials, meaning which polynomial is what's the evaluations of P plus Q, what would that be? That would just be the sum of these 2 vectors, right? So the evaluation of P plus Q is just P of alpha 1 plus Q of alpha 1 plus Q of alpha 2 plus Q of alpha n. So adding polynomials is just corresponds to adding their evaluations at these endpoints. Yes, there was a question here. Yes. Okay. So good question. So the question is, I said the representation of the polynomial p is p of alpha 1 to p of alpha n, the evaluations. I didn't say how we choose this alpha 1 through alpha n. So there's some freedom there, right? For any fixed choice, you could do the whole thing. So we have to agree on a convention saying, I'll give you the value of the polynomial at these points, at these values of alpha 1 through alpha n. So that's some choice we have in this picking alpha 1 through alpha n. You exploit that freedom later in the lecture. Any other questions? So this thing is almost a bit tautological, and it's like a lot of people immediately get it, and some people just miss the notation. So I just want to repeat this again. So what happened here is, instead of telling you the coefficients of the polynomial, I'm telling you the value of the polynomial. Okay? I'm telling you the value of p of 1, p of 2, p of n. And I'm telling you the value of q of 1, q of 2, q of n. Now, I ask you, okay, let's look at the sum polynomial, p plus q of x. What is its value at 1, 2, and n? Well, the value of p plus q of x at 1 is p of 1 plus q of 1. So you can just add the two values and get that. Right? So by just adding the evaluations corresponds to the evaluation of the sum of the two polynomials. Okay, so yes. Another question. I didn't specify what n is. Let's just assume that you have sufficiently many points that you uniquely identify the polynomial. So n is at least d plus 1, but it could be larger. You just have sufficiently many points that uniquely identify the polynomial. Okay? Any other questions on this? Yes.
Why is it advantageous?
Oh, why is it advantageous? Right. So it's right. So here it's not advantageous at all. Okay. So here the time it took was theta d. Okay. Right. It's not at all useful to look at this different representation, but let's go to multiplication and you'll immediately see. Okay. Let's do multiplication. Right. So now it's just super neat. Right. You have p is given by this vector, q is given by this vector. Okay, how do I calculate p times q? Well, I just need to multiply these two vectors entry-wise, right? So I just need to multiply p of alpha 1 times q of alpha 1, p of alpha 2 times q of alpha 2, then p of alpha n times q of alpha n. Okay. When you multiply polynomials, the coefficients get, lots of strange things happen to coefficients. The expressions are, take a long time to compute. But the values of the polynomial just multiply, right? So the values of p times q is just given by multiplying the value of p times the value of q. So you see that I just need to multiply these two vectors coordinate-wise. It takes theta n time, and we have the representation of p times q. Okay? Sorry? I'm sorry.
That process gives the same answer?
So this vector is the evaluations of the product. So it is the product in this representation. Right? So, yes, one question here.
So let's say you have like q n leading to 1 point for p. P times q will now be 2b.
Right.
But the vector is
Yes, I'll get to answer. Yes, I'll answer that question. Okay.
How do you account for degree polynomial?
Okay, great. So it's great. So one important detail that we have to worry about is when you multiply polynomials, the degree increases, right? So if you multiply a degree d polynomial and a degree d polynomial, you get a degree 2d polynomial, right? And suddenly you need more points to specify a degree 2d polynomial than to specify a degree d polynomial. For a degree d polynomial, you need d plus 1 points. For a degree 2d polynomial, you need 2d plus 1 points. So that seems to be an issue. But how do you fix it? Well, you start off with more points than you need. So you say n is more than 2d, right? You say n is more than 2d plus 2. Or let's just say n is 2d plus 2. Okay? Let's just start with more points, 2d plus 2 points. Then multiplication is super easy. You just multiply entry-wise, and then you get this, right? So if you didn't get this issue of now having enough points for the degree, don't worry about it. It's sort of a simple detail that you'll figure out by the end of this lecture. Yes. I'm just playing it safe. Yeah. Right. So the question was, why am I setting n to be 2d plus 2? It should be 2d plus 1. Yeah, you could have 2d plus 1. 2d plus 1 is sufficient. I'm just, having an even number over there. But you can set n, think of n as, let's say, 1000d. Right? You have sufficiently many points so that whenever you multiply things, you have enough points to uniquely identify the polynomial. Okay? And then the whole thing works out. Yes?
But what's the runtime to extract polynomial from this representation if you want to do a different
Great. Yes. Okay, so it's great. So the question now is, here's a situation now. We have two different representations of the polynomial, right? So one is coefficients, the other is evaluation, right? So the evaluations is, you just get p of alpha 1 through p of alpha n, and then you get q of alpha 1 through q of alpha n. Okay? Those are the two representations. And what we figured out is how much it takes in each of these representations. So this takes order d time, addition takes order d time, and multiplication takes order d squared. And in evaluation, the representation, the addition still takes order d time. And the surprising fact we sort of just noticed, it's order n time. Let's say n, think of n as order d always. N is 100d. Think of n as 100d for simplicity always. Okay? So the surprising thing that we just noticed is this square. In this representation, multiplication is linear time, which is kind of nice. But we really want to multiply polynomials in coefficient land, because our polynomials, a lot of the times, are given in terms of coefficients, and we want to work in that world. So if there is a easy way, if there's a quick way to go from coefficients to evaluations and back, if there's an efficient way to go from coefficients to evaluations and back, then you can start with coefficients, convert them to evaluations, multiply, come back to coefficients. That gives you a fast multiplication algorithm. So let me say that slowly again. So okay, so the idea for fast polynomial multiplication is just the following. So you get so your input is two coefficient vectors, p0 to pd and q0 to qd. These are two polynomials, p and q. what you do is you convert them into the other representation, which is its evaluations. So what you do is you somehow obtain evaluations of these vectors, these polynomials. We haven't seen how to do this, but suppose you could do this. Suppose you could convert them to the other representation. Okay? And then, of course, you can just multiply those two polynomials, and you get P of alpha 1 times Q of alpha 1, P of alpha 2 times Q of alpha 2, and so on, P of alpha n times Q of alpha n. So multiplication is easy there. And then what you do is you convert back to obtain the coefficients of P times Q. So your goal was to multiply two polynomials, and this is a plan to how to do it, right? If you convert it into the representation where multiplication is easy, do the multiplication and convert it back, okay? And you know that this operation is basically linear time. This is linear time. So if you could somehow achieve the conversion between the two representations quickly, you get a fast polynomial multiplication. And that's this conversion, we'll achieve that by what we'll call the FFT. We'll see more of that. But that will take d log d time. So basically we have reduced multiplication to this different question of converting between these two representations. And we'll see a nice algorithm to do that. Okay? Any questions on this? So this is how you get a fast algorithm to multiply polynomials. So, okay, so now really our question is, how do you go from one representation to another? But let's just do the simple thing first. How do you go from coefficients to evaluations? Okay, so I've written down the thing here. We'll go over it. Okay, so just to see what is your what's the setup? Well, the setup is as follows. You're given a polynomial P. Actually, let me okay, you're given some polynomial. I'm writing down a degree 4 polynomial there. Right, so you're given a polynomial. Okay, you're given a polynomial P, and you're given a bunch of points where you want to evaluate them. Okay, you're given a set of points. So let's just say my polynomial is 0 plus x plus 2x squared plus 3x cubed, and my set of points is, 5, 6, 7, 8. Okay? Okay, and it's sort of a useful thing whenever you're reading up a new algorithm. It's always useful to sort of run through the naive algorithm in your mind, or sort of understand what's the naive algorithm, to sort of know that, okay, I can do this given enough time, and of course now we are learning an efficient way to do this. Okay, it's clear that you can do this in time d squared, right? What do you do? Or n times d. What do? You just have to substitute 5, 6, 7, 8 in this polynomial, compute its value, and that's what P of alpha 1, P of alpha 2. So the naive algorithm takes nd time, and we know how to do that. Okay? The naive algorithm here is nd time. Okay, so let's see what we'll do now. So now we'll do something different. We'll try to use divide and conquer to speed up this computation. Okay? So when you think of divide and conquer, we could go two ways, or many ways, I guess, but two obvious ways is you could say, okay, I have n evaluation points, let me split it into two sets, divide that. Or you could say, I have a polynomial, let me split the polynomial into two smaller polynomials. Okay? You need to divide the problem somehow. So, I'm showing you the way which works, which is, let's split the polynomial p into two parts. And furthermore, we're going to split it with the odd parts, the odd degree coefficients in one polynomial and even one in the others. So here, we'll just, let's write down the odd degree coefficients, which is 1 and 3, right? So that corresponds to the polynomial z plus 3. And the even degree coefficients, these are 0 and 2. That corresponds to the polynomial, 1 plus 3z and 0 plus 2z. Right? Just put all the just split the polynomial into two polynomials by alternate coefficients. Okay? Okay, so now we have split the polynomial into two polynomials. 1 plus 3z. So basically, these two terms and these two terms. Okay? Sort of they went into different polynomials. Okay? So now, how do you get back the old polynomial from these two? Well, the identity that gets you back the old polynomial from these two is this. Okay? So why is this identity true? I'm going to tell you why the identity is true. You can also check it. It's not really hard to check it. You just check it. But it's not super important to know why the identity is true for now. Okay? Because it's just an identity, algebraic identity. If you expand out, you'll see that both left-hand side and right-hand side are the same. But why is it true? Well, what you're doing is you're taking p even and substituting x squared in place of x. When you substitute x squared in place of x, the coefficients get a gap of 1 in between them. So, and the same happens to p odd. So what you do is you take these vectors of half the length, create a gap in between them. When you multiply by x, you shift one of the polynomials, and you add them, you get back the old one. Okay, but this is just English, but maybe it's easier for you to just see the algebra, right? So one way to see it is, okay, let's just write down what if you write down what the right-hand side is and the left-hand side is, you'll see that the two sides are the same. So basically, let me just do it in this case. It is 0 plus 2x squared plus x times 1 plus 3x squared gives me p of x. Okay? In this example, that's what happens, and you can easily check that. Okay, so, that's some simple algebra. But given this equation, you see what's happening. If you want to know p of alpha 1, what you need to know is p even of alpha 1 squared and p odd of alpha 1 squared. Right? This equation is key for us. So what did we want to do? We wanted to compute p of alpha 1, p of alpha 2, p of alpha n. This equation tells us how to compute it. It says p of alpha 1 is actually equal to p even of alpha 1 squared plus p odd of alpha 1 squared. Sorry, alpha 1 times p odd of alpha 1 squared. Okay? So, the equation tells me how to calculate this. In order to calculate the left-hand side, I just need to calculate the two things in the right-hand side. So that's what I do recursively, right? This is how you do divide and conquer. You just split the problem, and you recursively solve the two parts. So I'm just going to recursively evaluate. I'm going to evaluate the polynomial p odd on alpha 1 squared, alpha 2 squared, alpha n squared. I'm going to evaluate the polynomial p even on, again, the squares. Right? And then, given these two, I can calculate the original values I cared about, which is here. P of alpha I is P even of alpha I squared plus alpha I times P odd of alpha I squared. Okay, so in this case, what ends up happening is you recursively calculate P odd of phi squared, P odd of 6 squared, P odd of 7 squared, and P odd of 8 squared. Okay? And then you similarly calculate the same things. Okay? You calculate these, recursively calculate this. Note that this is evaluating a polynomial of half the degree. Right? P even is a polynomial of half the degree because it only has half the coefficients. And P odd is a polynomial of half the coefficients. So that's nice. So somehow we've reduced the degree, but still have to evaluate at the squares of the points. We reduce the degree by 2, but now we have to evaluate the point, evaluate at alpha 1 squared, alpha 2 squared, alpha n squared. Okay? And this gives us an algorithm right now. Okay, so let's see how good that is. But before we do that, let's see if there's a question. Yes? Okay, so so the question was about how I got this P odd and P even. The question was about how I constructed these polynomials. Perhaps the simplest way to think of it is the following. If I give you any vector of numbers, you can convert it into a polynomial by putting increasing powers of z there. So if I told you 1, 2, 3, 4, the polynomial would be 1 plus 2z plus 3z squared plus 4z cubed. Okay? Any vector corresponds to a polynomial. A vector is if you treat a vector as a sequence of coefficients, you just put increasing powers of z, that gives you a polynomial. Okay? And so now what we did was we took the coefficient vector that we had of length d, we took alternating coefficients, d over 2 of them, put them in one vector, d over 2 in the other, and each of them we're treating as a polynomial. Okay? And so each of them is giving you this polynomial in z. Z is just some indeterminate. You could have used a different indeterminate. So I'm using a different. I'm just using a different indeterminate here. So what I meant here was P odd of z is equal to this. It's just a different. I didn't want to use x again because we're going to substitute z equal to x squared and could create confusion. So that's why I just use a different indeterminate. Just a different variable name. But z has, the variable names have no meaning in this entire exercise. Yes?
So out of curiosity, with the base case, with this recursive method, would it kind of stop when the given polynomial is of degree 1?
Yes. So the base case of this would be you have a polynomial of degree 1, let's say, and you want to evaluate it at n points. Right? So you still have some, okay, let me add a page. So the base case would look like, would look something like this. You're given some polynomial of degree 1. let me just say R of z is R0 plus R1z, some polynomial of degree 1. And then you still have n points, which are some powers of alpha. That's how the base case looks like. You want to evaluate this linear polynomial at n points. Okay? And how much time does it take? To evaluate like a linear polynomial on n points? Sorry? N. So, so the base case would take order n time here. Okay. Yes. Sorry? So the question was, why do we stop at degree equal to 1 and not degree equal to 0? You can go back and see that identity needs at least degree 1. Sort of it's, or if you, yeah. Any other questions on this? Okay, so all right. So we have some divide and conquer algorithm, which is a very natural divide and conquer algorithm, and let's try to calculate what its runtime is. Okay, and if you try to do this, unfortunately, it seems like there are two parameters at play here. One is the degree of the polynomial, which is d, and you have n points, alpha 1 through alpha n, where you want to evaluate it. Right? There are d and n, two parameters at play. So, but let's just write the recurrence in two parameters. Okay, so how would that go? Well, so if you want to analyze this, so t of n comma d, where d is the degree and n is the number of points of evaluation. Okay, what do you end up with? Well, by splitting the polynomial, we reduced the degree by 2, but we kept the number of points the same. Right? So you see that I needed to evaluate a degree d over 2 polynomial on n points. Alpha 1 squared, alpha 2 squared, it's still n points. So, and there were two such evaluations here. Evaluate p odd at n points, p even at n points. Right? So the two recursive calls give you 2t n comma d over 2, right? Plus, then, after you have these values of p even and p odd, you need to do this calculation at the end. And this calculation is, you see that it's roughly like 1 multiplication and 1 addition for each I. So that's n, order n. So you get the recurrence t of n comma d is 2t n comma d over 2 plus order n. Okay? And of course, t of 1 comma n, the base case is, t of n comma 1, we decided is order n. Okay? Okay? Yeah, yes. The question is, why am I keeping track of two variables if n is always a multiple of d? Well, because if you look at the sub-instances that we generated in the process, n was not a multiple of d at all times. The degree kept decreasing by 2 every time, but n stayed the same, which is kind of unfortunate, but that's what we have now. So this is the algorithm we have. Okay? And if you analyze this, I'll leave this as an exercise. But if you look at t of n comma d, what you end up with is order n times d. Okay? So you get an algorithm which is no better than the naive algorithm. The naive algorithm, if you want to evaluate a degree d polynomial at 1 point, it takes d time. Now, if you have n points where you want to evaluate it, it takes n times d time. So the naive algorithm takes n times d, and this also gives n times d. And but this, we'll see how to modify this algorithm a little bit, and it will give us the required runtime. So just one last question here. Yes. You do recursively. Yeah. Okay, so let's start in this case.